Hi guys, I hope this video finds you well. If you're watching this video, then more than likely you missed our Zoom meeting yesterday, and we really missed your presence there. But we are going to embark on our final journey of the year, and we are going to use modeling in Algebra 2 to look at real world situations. And while we've done that, little bits in the glimpses of our time together, I believe that this unit is the absolute most applicable regardless of whatever you're going to do after graduation. So I look forward to this journey with you, and we'll begin by looking at our final unit, which is exponential models. So I'm going to take a moment and share my screen so we can look at exponential models. Well, there's two different exponential models for us to look at. There's the growth model and the decay model. And so some of the applications for growth, for a growth model, is population growth. That's one of the major uses for a growth model in some sectors of the economy. You know, we might want to know, will our food supply be able to sustain the rate of population growth that we're experiencing? We may also want to know, especially when it comes to the tax base, you know, how is population growth going to affect how much taxes the government is collecting. Another use for the growth model is, you know, if science is near and dear to your heart, specifically anatomy or biology, some of the human sciences, then bacterial growth. You can model bacterial growth using exponential models that you learn about in Algebra 2. Another, maybe you say, Ms. Harrison, I really don't care about population growth. That's not something that I'm going to go into, you know, later in life, or I'm certainly not a science buff. But one of the other major applications that, regardless of what your plans are, what your desires are after graduation, that you can use growth modeling for is retirement. And I don't know about you, but Miss Harrison wants to retire at some point in time. I've got a lot of golfing and fishing to make up for in these work years, especially in the quarantine time of COVID-19. So with all that being said, those are applications for your growth model. Now, your decay model, where would you use a decay model? Well, one of the first things that come to mind is carbon-14 dating. So we use that in archaeology to try to see how old something is. But, you know, if I put back on my corporate hat, I was an accountant for years and years and years. And one of the major things that I was tasked to do in the accounting world is something that we call depreciation. And basically, that's a fancy word that says, as mechanical things, essentially, as mechanical things get older, then their value declines. So just think about that. You know, if you bought a car, like my car, her name is Bernice. So if I say Bernice, then you'll know that I'm talking about my car. So I bought my car in 2012 and love my car still. Bernice is going great. But the fact of the matter is that Bernice is not worth as much as she was when I first bought her, because she's got miles on her. You know, she's older, there's newer models out, and so therefore her value has declined. Well, that is going to be an example of a decay model. We have set formulas for each one, and so we'll go over those now. For a growth model, you've got the amount at any given time, which is simply a function. So we're used to seeing, you know, f of x. Well, that a of t is the same thing. It's just the amount at any given time is equal to the initial amount, small a, times 1 plus the rate of growth. That's what that R stands for. Close parentheses, all raised to the t, which is whatever your time period is. So if we were to write these down, we have essentially the future amount that we're solving for. And then we have initial amount, what we started with. R is your rate. That rate could be a growth rate. In this model, it is a growth rate because we're only looking at the growth model right now. But in your decay model, you're going to see that it could also be a decay rate. So we have the future amount is A of t, initial amount is A, the rate of growth in this situation is R, and then t is number of time periods. And so intuitively, if you think about growth models, then you're going to realize that you're expecting things to increase as time goes up. We call that a positive relationship. So if we were charting this on a graph, then we would have t on the y-axis or on the vertical and A of t on the horizontal. And just think about what we were saying, that we expect, with it being a growth model, we expect things to increase as time increases or as time goes by. So as time goes up, because we're at 1, 2, 3, 4, as time increases, we expect to increase on the x-axis as well. And so your growth model is going to look something like this. It could be straighter or flatter. Another example of a growth model is in sales. The sales industry is very large, and a lot of you will in some way, shape, or form be in sales. And so when a new product comes out on the market, for example, when this guy came out on the market and it was the absolute first time the world had ever seen an iPhone, people at Apple had to decide exactly how fast they thought that growth curve was going to be. And so to do that, they ran exponential models. How often, because they had to schedule their production to be able to meet the demand. And so as the new phones, the hype came out about Apple's launching a new product, something that we've never seen before, and they're going to continue to increase, and the buzz was there. Well, they had to be able to decide how many phones needs to be available at the release date, and how many phones do we need to have in production as our sales for our brand new product, the iPhone, increases. And so all of this is just an application of your exponential growth models that you're learning about here as a junior or a senior in Algebra 2. So this, I love exponential models. So that would be a growth model. Now let's look at the decay side of it. So let's look at the decay side. So all of your variables are going to be the same. There's one major difference between your growth and your decay. So I know we talked about carbon-14 dating, but another thing that decays over time besides cars is really bone density. So if you're a female, when you get older, your bones are going to start to decay. And so that's why, you know, a lot of experts will say that you need to start taking calcium. And then there's also, every time you think about taking one thing, there's always a risk factor. And so you have to depend upon your doctor to weigh your risk with with the benefits that you would receive from taking any supplement. But with that being said, bones do decay, especially among the female population. And so even bone decay rate is something that can be modeled given your genetic disposition with the decay exponential model in Algebra 2. So here we go. Let's look at it. So we have the future amount is still that A of t is equal to your initial amount times 1 minus, there's your difference, 1 minus r, all raised to the t. So that's your difference in your growth and your decay. Growth, you're adding. So that kind of makes intuitively sense because you're expecting things to grow. And how do you grow your paycheck? You keep adding to it, right? When you're expecting things to decay or decline, then how do you cause something to decrease, decay, decline? It's all those DE prefixes. And so therefore you subtract. So that's your major difference, is that you're going to subtract the rate of decay as opposed to adding it in your growth model. All right, so there's our differences. Now let's look at application. Just real quickly, a sketch of a decay map. You still have t on your vertical axis and A of t on your horizontal. And basically when you're expecting things to decrease, that means that as time increases, you expect your total amount to decrease. So as you're going up on the vertical, you're expecting to go down, working towards the origin on the horizontal. And so that means you're going to start at a higher rate and wind up at a lower total amount. And so you're going to have higher to lower. You know, your decline is going to look, well, I just drew that absolutely backwards. Scratch that out. I was still on my growth brain. So time, A of t, 1, 2, 3, 4, 1, 2, 3, 4. So still, as you expect time to go up, you expect the value to go down. And so you're going to start high and end up low. So you can see the difference between the two. Start high, end up low. So your slope here would be negative, and your slope here would be positive. So there you go. And that makes intuitive sense. Remember, start high, end up low, or start low and end up high. One is, unfortunately, how our cars depreciate. The other one, the positive slope, is definitely how we hope our money will grow if we invest it wisely. So now let's look at some specific examples. And in topic 6.1, in topic 6.1, you have a population growth situation where the current population is 4.6 million. And you anticipate the population to grow at 1.3% per year. And this is the population in 2010. And so we are asked to find what would the population be in 2014. Well, we're going to do this in a step-by-step situation, and then I'm going to show you how to do it all in one step. So multi-step versus one step. Go back to our growth model. The future amount is equal to the current amount times 1 plus r raised to the t. And we're going to put our years here, 2012, 2013, 2014. And right now we're at 4.6 million. So this is year and population. And so to do this step by step, we've got A of year 1, which is 2011, is equal to the population in 2010, that's your initial amount, 4.6, times 1 plus your growth rate, which was 1.3%. We can't add a whole number in a percentage. We have to convert the percentage to a decimal. And so if you remember, 1.3% is equal actually to 1.3 over 100. That's what a percent all is. So to convert this to a decimal, you simply move your decimal in the percent form over 2, 1, 2. So we've got 1.3, 1, 2, put the decimal there, fill in with a 0. And so our percent, our decimal form of the percent is 0.013. And that's what we have to put up here, 0.013, our decimal form. And we're only going 1 year into the future. And so we're going to raise that to the 1. So now we can simplify this down to 4.6 times 1.013 raised to the 1. I'm going to get out my handy dandy calculator. So here we have 4.6 times 1.013. And that gives us a population in 2011, which is our first year over here, of 4.6598. So now we want to find the population. So this is 2011. Now we're going 1 more year into the future, and that's why I've left this at 1, because our base has changed. Our initial amount, we're going to use what we calculated here, that 4.6598. So in 2012, we're going to go 1 more year in the future. We're going to take the initial amount that we just calculated in 2011, right here, 4.6598 times 1.013 raised to the 1. And that's going to give us our 2012 amount. So to keep from making any type of rounding errors, I'm just going to leave that number that we just calculated in the calculator. So I'm simply going to say times, it brings my answer down, 1.013, and that's still raised to the 1, so that I don't really need to put that. And that gives me 4.7204 if we want to round it just to right. But in actuality, I'm not going to take that number out of the calculator, because otherwise that encourages rounding errors when we do this in a step-by-step function or process. So I'm just going to leave that in there for now, set it over to the side. and say this equals 4.7204. Now we're going to look at 2013, which is one more year into the future, and we're going to use this amount for our initial starting amount, 4.7204 times 1.013 raised to the 1. Once again, to keep from making any rounding errors, I'm leaving that in my calculator, times 1.013, and that gives you 4.7817. We'll truncate it there, but we're going to leave it into the calculator. We're not going to take it out. So 4.7817, put that in our chart up here. And then finally, 2014, which is the actual year that we were looking for to start with. So we're going one more year into the future. We're going to use the amount that we just calculated for 2013, 4.7817 times 1.013 raised to the 1. Bringing it down from my calculator again, 1.013. And that gives us a population in 2014 as 4.8439. So 4.8439. And we can put that here. Now let's do some double checks. Let's look at some things. We know that this is a growth model, or at least that's what we were told, population growth. So let's look at our calculations. We've got 4.6, 4.65. Did it go up? Yeah, it did. 4.65 to 4.72. Is that an increase? Yes. 4.72 to 4.78. Once again, that's an increase as well. And then finally, 4.78 to 4.84. Yes. So this intuitively makes sense. That's just double checking, not necessarily our specific calculations, but whether or not our calculations make sense given our model, which is always important, especially when you're dealing with real world situations. Now, I promised that I would show you the one-step approach. So the way that we could do this is we started in 2010, and we were asked to find the population in 2014. That is simply 1, 2, 3, 4 years into the future. 4 years into the future. So with that being said, we can set up, we know that our T is equal to 4. Our A is where we start with in 2010, 4.6 million. And so we can say A of 4 is equal to 1 plus 0.013 raised to the 4. And so that is A to the 4 is equal to 1.013 raised to the 4. And this is just a one-step process now. So we can take our calculator, trying to get it where you can see the formula and calculator. So we can take our calculator and we have 4.6, which is what we started with, times open parentheses. I like to use my parentheses because it makes sure that the calculator knows exactly what you mean. The calculator is not a mind reader. And sometimes just by entering it into the calculator incorrectly, then it messes up our whole calculation. And that's another reason why it's important to go back and check for, does your answer make sense based upon what you were asked to find? So we have 1.013 raised to the 4. Then I'm going to arrow over to get out of the exponent, close parentheses equals, look at there, the exact same number from going step by step or doing the one step. So check, we match. And that's one of the reasons why I said make sure when we were doing all of those step by steps to leave those answers into your calculator, because otherwise if you did not, if you only pulled out what we wrote down in our table, then you're going to have some rounding errors. So be aware of that, and don't fret. You may wonder, how does this compare to population growth over the US? And we could even look at the world. And so one of the things that, I like to look at in real life scenario is you can look at, so this screen right here that shows you the population growth from essentially the 1900s all the way up to 2020. So there's your population growth. I really like, this is actually put out by the S&P 500, and they have compiled this data from census data, which of course we're in a census year, and even though I don't like having to fill out more paperwork, I can see the value of it because of this data right here that I do like to look at. But you can see when population declined here, that was when we entered World War I. When population growth kind of stagnated a little bit right here, you'd have to zoom in really close to be able to see it. Then that was when we were in World War II, and then we had a huge jump, and we know that as the baby boomer generation. And so that's some interesting data. Some other data that you can look at is this population clock, which is also generated by the U.S. Census Bureau. And so this population clock, you can see that the U.S. population is essentially growing by 3 people every minute. And we know that because right down here it says net gain of 1 person every 20 seconds. There's 60 seconds in a minute, so 60 divided by 20 or 6 divided by 2 is 3. So we're adding 3 people to the population every minute in the U.S. But look at the world. Look at how fast the world population is increasing. One of the things is that the U.S. is only a very small part of that, and you've got all these other countries that their populations are increasing, so you have to add them all together to get the world. And so of course you're going to expect that world clock to be cranking fast. But it is interesting to just look at population growth models and how they are growing and how the U.S. is comparing to the rest of the world. So that is all for example 3 from topic 6.1. I'm going to stop it here and see you in just a second with example 2.